Hello students, welcome to our physics class. Today we are going to learn Bernoulli's theorem. So before going to learn the Bernoulli's theorem, we should know the equation of continuity. Here we are going to discuss about the mass flow rate of liquid that can be called as volume flux or flow rate, mass flow rate of liquid. Okay, we should consider steady flow. Incompressible liquid flows steadily. So consider a pipe AB. Consider a pipe AB. So this is pipe A and this is pipe B. Okay. So this is A pipe and this is B pipe. It has the area of cross section A1 and A2. Here A1 is greater than A2. A1 is greater than A2. And the liquid is non-viscous liquid and incompressible liquid and flows steadily. So what the liquid? It is non-viscous liquid and incompressible liquid and flows steadily through the pipe. The velocities V1 and V2. Velocities at the pipe A1 is A is V1 and velocity at the pipe B is V2. Here we are going to find out the mass flow rate. So first the mass of the flowing liquid through a section A we are going to find. Here we are using the formula for mass as mass is equal to density into volume. Density is equal to mass per volume or mass is equal to density into volume. Okay. Also the volume can be written as area into height. Area into height, or we can write area into distance. Again, we can write the mass is equal to density into area into what is distance? Velocity into time. Velocity into time. This is the formula we are going to use for finding mass. Okay. So mass is equal to density into volume. Density into volume can be written as area into distance and distance can be written as velocity into time. Now let's find the mass M1 of fluid flowing through a section A in time delta T is. Okay. So M1 is the mass of flowing liquid through a section A. Through a section A in time delta T. Can be written as density is rho. The density of the liquid is considered as rho and area at the section A1 is A is A1. Velocity at the section A is V1 and the time delta T. Understood? So what is M1? M1 be the mass of flowing liquid through a section A in time delta T. This can be written as M1 equal to A1 V1 delta T into rho, where rho is the density of the flowing liquid. Similarly, we can write mass M2. M2 be the mass of the flowing liquid through a section B in time delta t. That also can be written as, in B section, A2 is the area, V2 is the velocity, and delta t is the time, the density is rho. So M2 is equal to A2, V2, delta t, rho. In an incompressible liquid, mass is conserved. Okay? Mass is conserved. So we can have M1 equal to M2. M1 equal to M2. So I can write M1 is A1 V1 delta T rho equal to M2 is A2 V2 delta T rho. So here delta T get cancelled, rho get cancelled. We are getting A1 V1 equal to A2 V2. Can be written as AV. That is equal to constant. Okay. So A1 V1 equal to A2 V2 equal to AV is equal to constant. This is known as equation of continuity. This is called equation of continuity. Actually, it is obtained from the conservation of mass. Okay. Conservation of mass in the flow of liquids. We are getting the equation of continuity as AV is equal to constant. So it can be said as volume flux or flow rate remains constant. What is the name? Volume flux or flow rate remains constant. What do you understand from this formula? A is inversely proportional to V. Am I right? A is inversely proportional to V. It meant that smaller the cross section, smaller the area of cross section, greater will be the velocity of the fluid. Okay? A is inversely proportional to velocity. So we can write smaller the cross section, greater will be the velocity of the fluid. So this is about equation of continuity. Now let's see the Bernoulli's theorem. This theorem was explained by Swiss scientist Daniel Bernoulli in the year 1738. He has found out the relationship of flow of liquid through a pipe of varying cross section. He found out the relationship of flow of liquid through a pipe of varying cross section based on the law of conservation of energy. Let's see the statement. According to Bernoulli's theorem, the sum of pressure energy, kinetic energy and potential energy per unit mass of an incompressible non-viscous fluid in a streamlined flow remains constant. This Bernoulli's theorem. According to Bernoulli's theorem, the sum of pressure energy, kinetic energy and potential energy per unit mass of an incompressible non-viscous fluid in a streamlined flow remains a constant. Mathematically, we can written as P by rho plus V square by 2 plus GH is equal to constant. P by rho plus V square by 2 plus GH is equal to constant. This is Bernoulli's equation. Okay, this is known as Bernoulli's equation. Let's see the proof of this theorem. Let us consider a pipe AB of area of cross section AA and AB. So this is the pipe AB. Which is at a height h1 from the ground and h2 from the ground. So A is at a distance h1 from the ground and B is at a distance h2 from the ground. Now we have considered an incompressible, non-viscous, streamlined flow of liquid in this pipe. Let AA be the area of cross section at the section A, and VA be the velocity of the liquid at the section A. Similarly, AB be the area of cross section at section B, and VB be the velocity of the flowing liquid at the section B. Similarly, we can consider here pressure at the section A is PA. Force exerted by the liquid at the section is FA. And here also pressure exerted is PB and force exerted is FB. Now, capital V be the volume of the liquid. This volume of the liquid is same when it enters at A and which is leaving from B in the same time. Okay, so V be the volume of the liquid when it enters A in a time t, which is equal to the volume of the liquid leaving B in time V. Now let's write the pressure energy. So first, before going to write the first pressure energy, we are writing the force exerted by the liquid at A. Force exerted by the liquid at A can be written as FA. FA is equal to pressure into area. So PA into AA. Now the distance travelled by the liquid in time t is taken as d. D is equal to velocity into time, VA into T. Here we are going to write the pressure energy. So instead of writing energy, we can find out the work done. Work done is equal to energy. Right. So what is work done formula? WA is equal to force into distance. Am I right? So FA into D. This is actually equal to energy. So FA is PA into AA and D is VA into T. So PA, AA, VA into T. Here we can have AA, VA, T. That is AA, VA, T can be written as AA into D. That can be written as volume. Area into velocity into time. Velocity time is distance. Area into distance is volume. Okay. So AAD is equal to V. That is equal to volume of the liquid entering at A. Volume of the liquid entering at A. Now the work done. What is work done? Work done is the pressure energy. This is work done, that is equal to pressure energy. So that is equal to FA into D is equal to PA into V. Understand? So W is equal to PA, AA, VA into T. Here instead of AA, VA into T, what we have substituted? Capital V, because area into velocity into time. Velocity in time is distance. So area into distance is volume. So work done or pressure energy can be written as PA into V. Now pressure energy per unit mass. Actually in the Bernoulli's theorem we have got it. The sum of the kinetic energy, potential energy, pressure energy per unit mass of an incompressible liquid remains constant. So we are going to find out first pressure energy per unit mass. Pressure energy per unit mass. at A can be written as, that we can denote as EPA. Okay. It is energy due to pressure at the position A is equal to pressure energy per unit mass is, what is pressure energy? Work done. That is PA into V divided by M. Pressure energy per unit mass. So PA into V divided by M. This can be written as PA divided by M by V. This V we can write in the denominator. That can be written as PA by rho. Okay. So this is V, capital V, and mass per volume is density. Mass per volume is density. So we can write as PA by rho. So this is about pressure energy per unit mass. When we are writing pressure energy alone, that is pressure energy of the liquid at A is, pressure energy of the liquid at A is, that is EPA is equal to PA into V. Am I right? PA into V. This again we can written as multiply and divide by M by M. M by M. Okay. Now this can be written as PA into M divided by M by V. That is equal to, what is that? PA into M divided by rho. M by V is rho. That is pressure energy at A is EPA is equal to MPA by rho. Similarly, we can write for potential energy of the liquid at A and kinetic energy of the liquid at B. Okay. So what is potential energy? Potential energy of the liquid at A is P, potential energy. So PE at A is equal to mgh. mgh h1, or we can consider as HA. Okay. Here the height at A is taken as HA, height at B is taken as HB. So we can write mgha. Next, kinetic energy. So because of the flow of liquid, it possesses kinetic energy. So what is kinetic energy at A? Kinetic energy at A is, that is KE. KE at A is equal to half mv square. So half mva square. Half mva square. So pressure energy at A is EPA equal to MPA by rho. Potential energy at A is PEA equal to MGHA, and kinetic energy at A is KEA is equal to half mva square. So what is the total energy due to the flow of liquid at A? Sum of these three. So total energy of the liquid flow at A is equal to EA. EA is equal to pressure energy plus potential energy plus kinetic energy at A. So when we substitute, what we will be getting? EA is equal to MPA by rho plus half MVA square. Sorry, this is kinetic energy, and plus MGHA. Okay, so this is the total energy due to the flow of liquid at A. Similarly, we can write the total energy at B. That is, AB be the area of cross section at B, VB be the velocity at B, PB be the pressure exerted by the liquid at B. So calculating total energy at EB. So similarly, the total energy at B is What is that? EPB. Pressure energy at P plus potential energy at B plus kinetic energy at B. So we can have the same formula. EB is equal to MPB by rho plus half MVB square plus MGHB. Okay. So now, according to the law of conservation of energy, this Bernoulli's theorem is based on the law of conservation of energy. So according to the law of conservation of energy, the total energy at A is equal to total energy at B. Am I right? Total energy remains constant. So from the law of conservation of energy, what is that? EA is equal to EB. So substitute the values. What is EA? MPA by rho plus half MVA square plus MGHA equal to MPB by rho plus half MVB square plus MGHB. Okay. Now all the terms M is there. So if you take M as common outside this side, PA by rho plus half VA square plus GHA is equal to. Here also we can take M as common outside. PB by rho plus half VB square plus GHB. So M gets cancelled. We can have the equation PA by rho plus half VA square plus GHA is equal to PB by rho plus half VB square plus GHB. Okay. So that is equal to constant. So right hand side and left side remains same. So we can write that is equal to constant. So the above equation can be written as generally P by rho. P by rho plus V square by 2 plus GH is equal to constant. So this is known as Bernoulli's theorem or Bernoulli's equation. This again can be written as, when we divide the equation by G, we will be getting P by rho G plus V square by 2G plus H is equal to constant. In case the height H is equal to 0, that means when we consider the horizontal pipe, so H is equal to 0. So we will be getting the answer as P by rho G plus V square by 2G is equal to constant. Okay, I repeat, listen once again. Bernoulli's theorem. According to Bernoulli's theorem, the sum of pressure energy, kinetic energy and potential energy per unit mass of an incompressible non-viscous in a streamlined flow remains constant. That is P by rho plus V square by 2 plus GH is equal to constant. So we have the proof as, consider the pipe AB which contains the incompressible non-viscous streamlined flow. The positions A and B are at a height HA and HB from the ground, and AA be the area of cross section at A, AB be the area of cross section at B. VA be the velocity of flow of liquid at A, VB be the velocity of flow of liquid at B. Similarly, FA and PA are the force and pressure at A, FB and PB are the force and pressure at B. So first we have to find out the pressure energy. Before that, force we can write as force is equal to pressure into area, and distance traveled by the fluid we can write as distance is equal to velocity into time. So pressure energy means nothing but work done. Work done is equal to force into distance. So force PA, AA, distance VA into T. Now instead of AA, VAT we can write capital V because area into distance is equal to volume. Now pressure energy can be written as work done is equal to force in distance or PA into V. Okay. Pressure energy per unit mass means we have to divide by M. So we will be getting PAV by M, or else PA by M by V, or PA by rho. Now we can write pressure energy alone. Pressure energy at A means EPA is equal to PA into V. When we are multiplying and dividing by M, we can rewrite PA into M by V. So M by V is rho. We can write PA M by rho. So pressure energy at A is EPA is equal to MPA by rho. Potential energy at A is PA is equal to MGHA. Kinetic energy at A is KA is equal to half MVA square. So total energy at A is EA is equal to EPA plus PEA plus KEA. So we are substituting MPA by rho plus half MVA square plus MGHA. Similarly, we can write for EB, total energy at B, EPB plus PEB plus KEB. If you substitute all those values, we can write MP by rho of MVB square plus MGHB. So according to law of conservation of energy, we can write EA is equal to EB. So when we write all the values, M get cancelled. So PA by rho plus half VA square plus GHA is equal to PB rho plus half VB square plus GHB is equal to constant. So P by rho plus V square by 2 plus GH is equal to constant. Generally we can write. Again, if we divide the whole equation by G, we can write P by rho G plus V square by 2G plus H is equal to constant. Suppose the pipe is horizontal, H is equal to 0. So we can have P by rho G plus V square by 2G is equal to constant. And listen one more point. Here we are considering the streamlined flow. Isn't it? So this equation only valid for non-viscous, zero viscosity and streamlined flow, because we are using the conservation of law of energy. That is, there is no loss of energy, but in practice some energy get lost due to friction, isn't it? So because of friction some energies are lost, so it exerts some loss of energy, means the loss of energy is converted into heat energy. But here this equation only strictly valid for zero viscosity and non-viscous liquid. Understand? Okay students, now let's see the applications of Bernoulli's theorem. First, blowing of roofs during windstorm. So in olden days, the roof of the huts or house were designed with a slope. We know that, isn't it? This is the slope as shown in this figure. One important scientific reason is that as per the Bernoulli's principle, it will be safeguarded except roof during the storm or cyclone. How it will be safeguarded? So listen, there is a wind flow in this direction. The pressure will be acting on the roof as well as from bottom of this roof. So P1 and P2. So during the cyclone condition, when the high wind flowing over this roof, it creates a low pressure difference. Okay, so here when the high velocity of flow is there, it creates a low pressure. So in order to balance here, the pressure under the roof is greater. So there is a pressure difference. Understand? So it creates a upward force. So the roof is blown off. That is, during cyclone condition, the roof is blown off without damaging on other parts of the house. In accordance with the Bernoulli's principle, the high wind blowing over the roof creates a low pressure. Okay, so here the velocity and pressure is inversely proportional. Keep it in mind. Pressure and velocities are inversely proportional. So, high wind blowing over the roof creates low pressure P1. The pressure under the roof P2 is greater. Therefore, the pressure difference P2 minus P1 creates an upthrust. The roof is blown off. The next one is aerofoil lift. Okay. So, the wings of an airplane are so designed that its upper surface is more curved than lower surface. You all know that. Upper surface is more curved than lower surface. And the front edge is broader than the rear edge. As the aircraft moves, the air moves faster above the aerofoil than at the bottom. Look at this figure. So this is the shape of this air wings. Here, this is more curved than this bottom. Okay. Now, aircraft moves, the air moves. Okay. Air moves faster above the airfoil. So, the velocity becomes high than at the bottom. So, according to Bernoulli's principle, what will be happen? The pressure of air below is greater than the above. Because here the velocity is more, so pressure is less. Here the velocity is less, pressure is high. So it creates an upward force, upthrust, called the dynamic lift to the aircraft. The next one, Bunsen burner. Here, the chemistry lab, you may have seen this Bunsen burner. The gas comes out of the nozzle with a high velocity. Hence, the pressure in the stem decreases. So, outside air reaches into the burner through an air vent, and the mixture of air and gas gives a blue flame as shown in this figure. So, this is the Bunsen burner, and here there is a air hole. Okay. So, the pressure in the stem decreases when the gas comes out of the nozzle with a high velocity. If there is, here there is a nozzle hole. So, the gases will come out with a very high velocity. So, here the pressure decreases. But from outside the air will be reaches into this burner. Okay. So, now the mixture of air and gases gives a blue flame in this Bunsen burner. The next one is venturimeter. Listen, venturimeter is used to measure the flow speed, that is rate of flow. It is used to measure the rate of flow or flow speed of the incompressible liquid through a pipe. So, what is the principle of this? Venturimeter is Bernoulli's theorem. So, venturimeter is application of Bernoulli's theorem. So, it works on the principle of Bernoulli's theorem. So, this consists of pipe A, two wider tubes A and A dash. So, this is A and this is A dash. This is connected by means of a narrow tube that we can consider as B. Okay. There is a manometer. Manometer in the sense it is in the form of U tube. Okay. So, this is attached between the wide and the narrow tube. So, these two are wider tube and this is the narrow tube. So, a manometer is attached between the wide and the narrow tube. Here, the manometer contains the liquid having the density as rho. So, rho is the density of the liquid, or else we can write rho m. That is manometer. Okay, the manometer contains the liquid density as rho m. Here P1 be the pressure. P1 be the pressure of the liquid in this wider tube. Okay. Now the density of this liquid is rho and the velocity of the liquid at this wider tube is V1. When it enters into the narrow region, narrow region, its speed increases to v2. The velocity is increases to v2. So here there is a increase in speed. That means it creates a pressure difference. Increase in speed, that means it creates a pressure difference. So pressure in this narrow region is taken as P2. Okay. Now there is a pressure difference between the tube A and B. So the pressure difference is taken as delta P is equal to P1 minus P2. So the velocity increases from V1 to V2. So the pressure is decreases from P1 to P2. So pressure difference is P1 minus P2. How can we calculate this pressure difference? That is calculating by means of the height differences in the manometer. So this is the height difference, H. Okay. So by measuring the height differences between the surface of the manometer liquid, we can calculate the pressure difference. Now let's write the equations. According to equation of continuity, what is equation of continuity? AV is equal to constant, am I right? So area into velocity is equal to constant. So at the wider region, we can write the area as capital A and the velocity as V1. That is equal to, in the narrow region, the area we can consider small a and the velocity as V2. So a V1 equal to small a V2. From this we can write V2 is equal to a into V1 by small a. So what Bernoulli's theorem says? According to Bernoulli's theorem, that is P by rho plus or P by rho g plus V square by 2g plus h is equal to constant. This is about the Bernoulli's theorem. Am I right? Or else P by rho plus V square by 2 plus gh is equal to constant. Here the horizontal pipe, so h we can take as 0. From this we can write P plus rho into V square by 2 equal to constant. This also we can write. So accordingly we can write here in this venturi meter, P1 plus rho into V1 square by 2 is equal to P2 plus rho into V2 square by 2. Okay, in that venturi meter pipe, P1 plus rho V1 square by 2 in the wider tube is equal to P2 plus rho V2 square by 2 in the narrow tube. So if you substitute V2 from this equation, V2 is equal to what? A V1 by A. So you will be getting P2 plus rho into, instead of V2 square, that is 1 by 2 into V2 square is nothing but A V1 by A the whole square. So from this we can write P1 minus P2, pressure difference. Pressure difference. So this is P1, this is P2. We can write delta P is equal to P1 minus P2 is equal to, what is that? Here already rho into B1 rho by 2 into A V1 by A the whole square minus this one is rho V1 square by 2. So we can write rho into V1 square by 2 as common outside, and here capital A square minus capital A square by A square minus 1. Or else we can write rho V1 square by 2 is equal into A square minus A square by A square, cross multiplication. Okay. So from this we can easily calculate the flow speed or speed of flow of liquid at the wide end of the tube. That is V1 square alone we can keep this side. So here 2 into delta P divided by rho into, here this a square will go numerator and here a square minus a square. Understand? So how can we write? V1 square is equal to 2 delta P a square divided by rho into a square minus a square. So from this, what is V1? V1 equal to square root of 2 delta P into a square divided by rho into a square minus a square. So this is the velocity or the speed of flow of liquid at the wide end of the tube. From this we can calculate the volume also. What is the volume of the liquid flowing per second? Volume of the liquid flowing per second is taken as capital V. Capital V is nothing but volume is equal to area into distance, that is area into distance is equal to velocity into time, isn't it? So here we are going to find out the volume of the liquid flowing per second. Per second means we can write A V T by T. T get cancelled. So we can write area into V. So here the volume of the liquid flowing out per second is V is equal to A into V1. Here V1 is the velocity at the section A. So we can have A into, what is V1? Root of 2 into delta P A square divided by rho into A square minus A square. So this is about Venturi meter. So Venturi meter is used to find the flow of speed of liquid, flow of liquid speed. Okay. Other applications also given, that is the Bernoulli's concept is mainly used in the design of carburetor of automobiles, filter pumps, atomizers and sprayers. For example, the carburetor has very fine channel called a nozzle through which the air is allowed to flow in larger speed. In this case, the pressure is lowered at the narrow neck and in turn the required fuel and petrol is sucked into the chamber so as to provide the correct mixture of air and fuel necessary for the ignition process. Today we have discussed about state the principle and usage of Venturi meter, obtain an equation of continuity for the flow of liquid on the basis of conservation of mass, state and prove Bernoulli's theorem for the flow of incompressible, non-viscous and streamlined flow of liquid. This is an important question. And describe the construction and working of Venturi meter and obtain an equation for the volume of liquid flowing per second through a wide entry of the tube. So these questions learn well. Thank you, students.